right? So let me explain you about the page replacement algorithms first. So whenever there is a page fault, what is a page fault? Whenever the required page is not available in the main memory, then it is called as page fault. So at that time what you have to do, you need to keep the required page into the main memory frame. At that time there is no free frame. I repeat, whenever you require a page, that page is not available in the main memory, then it is called as page fault. You need to bring that particular page, required page into the main memory, okay, main memory frame. But there is no free frame. Already some pages are occupied the main memory frames. At that time, what you need to do? You need to replace the required page with the page already in the main memory. Okay. So which page you need to consider as a victim? Which page you need to draw from the main memory in order to keep in the or bring in the required page into the main memory frame? Which frame? Which page you need to brought out from the main memory to secondary memory, right? So that where we require page replacement algorithms. Okay, we have a first in first out page replacement algorithm. In this, the frame, for example, here three frames are there. Follow the cursor. So initially we require a seventh page. Seventh page is not there in the main memory, so there is a free frame. So no need of page replacement algorithm. You can keep 7. After that, what you require? 0. Right? 0 is also not there in the main memory, right? But there is a free frame, so we can keep the page into the main memory. After that, we require page number 1. Page number 1 is also not there in the main memory. What you need to do? You need to keep page number 1 into the main memory, and there is a free frame. So up to these particular mm, uh, three parts, sorry, three references from 7 to 1, up to these three references, there is a free frame in the main memory, so that whenever there is a page fault, you can keep the or brought in the page into the main memory. After that, whenever you require a second page, page number 2, that is not there in the main memory, what you need to do? You need to bring the page number 2 into the main memory. But the 7th page and 0th page and first page are already occupied the 3 frames, so there is no free frame at this point. So what you need to do? There is a page fault. Why? Because 2 is not there in the main memory. We require 2, so that is a page fault. Whenever there is a page fault, so automatically what you need to do? You need to keep the or brought in the page number 2 into the main memory, but there is no free frame in the main memory. So at that point, you need to brought out either 7 or 0 or 1 from the main memory. Which one you need to select as a victim page in order to bring in the second page into the main memory. So if it is a FIFO, 701 is already there in the main memory. So what you need to do? Which one came into the main memory first? 7 came into the main memory first. So first in and first out. The page which is came into the main memory first will brought out from the main memory first. So obviously, so we take out the 7 from main memory and we brought in the second page into the main memory. And what you require next? 0. 0 is already there in the main memory, so there is no page fault. Okay. After that, 3. Whenever 3 came into the picture, okay, so there is a page fault. Why? Because we require third page, but third page is not available in the main memory. Page number 3 is not there in the main memory. Okay. So at that time, what you need to do? Either you need to take out 2 or 0 or 1 from the main memory, and you need to brought in the third page into the main memory. So you need to select 2, 0 or 1 as a victim page. So which one came into the main memory first? Among these three, 0 came into the main memory first, right? That is the reason why you replace 0 with 3. Okay, that is about FIFO. Okay. What about the optimal page replacement algorithm? And the next page replacement algorithm is optimal page replacement algorithm. In the case of optimal page replacement algorithm, so whenever there is a need, for example, at this point, observe at this point, so you require fourth page. You require fourth page, but there is no free frame. 203 are there in the main memory. 203 are in the main memory. You require fourth page now. So which one you need to take out according to the optimal page replacement algorithm? So the page which is will not be used for longest period of time. Follow the cursor. The page will not be used for the longest period of time. That means you need to check in this direction. Follow the cursor. You need to check in the direction, right? So you which page you need to select 2, 0 or 3. Which one we need to select as a victim? After 4, immediately we require 2. So we should not choose 2. After the page 2, you require page 3. Immediately after 2. So we should not choose page 3. After that, we require 0. 0th page. That is the reason why 0th page is the victim page. So I replace 0 with the 4. Okay. After that, 2 is already there in the main memory. 3 is also there in the main memory. And next, now you require 0. 0 is not there in the main memory. So what you have to do? 2, 4, 3. Which one you need to consider as a victim page? After 0, 3 I require. And then later I require 2. And then 4 is not required at all. After page 0, so I require 3, I require 4 in the near future. But 4 I won't require for the longer time. Not at all required, right? That is the reason why 0 is replaced by 4. Okay. And then 2 is already there in the main memory. 3 is also there in the main memory, right? No page fault. So whenever 1 is required, page 1 is not there in the main memory. So 203, which one I need to take out? So after 1, immediately I require 2. After that I require 0. 3 I don't want anymore. So that is the reason why I replace 1 with a 3. Okay. After that, 2 is already there in the main memory, 0 is already there in the main memory, 1 is already there in the main memory, no page faults. And whenever there is a need of a 7th page, page 7, so 7 is not there in the main memory, so page fault. And there is no free frame. 201 are occupied the free frames. So what you have to do, you need to select one page. Which page you need to select? After 7, I need 0, 1, but I don't require 2. That is the reason why I replace 2 with the 7th page. That means in order to perform optimal algorithm, you need to know the future requirement. What is your future requirement? For example, now here 0 you want to keep into the main memory. Which one you need to take out? That will be decided by the future reference string. So which one you require next? Upcoming pages requirement you need to know. So that is a major problem in the optimal algorithm. Here, can't read the future. We cannot know right now what are the pages we require afterwards. Right? So future references we might not know at current position, right? So that is the problem with optimal page replacement algorithm. What is the problem with the first in, first out? So the last one, Bellardi's anomaly. Bellardi's anomaly means, so actually Bellardi's anomaly means here we have 3 free frames, right? In this example, for each process, we are assigning 3 free frames. If you are increasing free frames to 4 frames, if we are giving only 3 frames for a process, the number of page faults are 15. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 page faults are there. In the case of FIFO, if we assign 3 process, if we allocate 3 free frames for the process, 3 frames, that means we can keep 3 pages of a process. So if we increase the free frames to 4, what happened? So what will happen? So if we increase these 3 frames to 4 frames, the number of page faults need to be decreased. But in the case of FIFO, adding more frames can cause more page faults. If we adding more frames, actually more free frame if we add, the number of page faults need to be reduced. But here in the case of FIFO, if we add more free frames, the number of page faults are increasing. So that problem is called as Bellardi's anomaly. That is the problem with first in, first out. Very important question, Bellardi's anomaly. Bellardi's anomaly means adding more frames causes more page faults. Rather than reducing the reducing the number of page faults, adding more frames will increase the number of page faults. So that is the problem with FIFO. So what is the problem with optimal page replacement algorithm? So we need to know the feature reference. That is the problem in optimal algorithm. So what is least recently used? For example, go to this location. Go to this location directly. Follow the cursor. So 203 are there in the main memory free frames. Now you need to keep the 4. So which one you need to replace? For this purpose, you need to know the past history. You need to know the past history. Which one was just came into the main memory? Which one was just came into the main memory? Which page which page was used very recently, right? So 4 is you need to 4 is the page required, but there is no free frame. So 203 are in the main memory. You need to consider one page as a victim page. Before 4, just 0 you referred. Before 0 you referred 3, and then 2 you referred long back. When compared to 0 and 3, you referred to long back. So that is the reason why 2 will be replaced with 4. Okay, and then again you require second page. Again you require second page. What you need to do? You need to select one frame from 403. 4 just came into the main memory. Before 4 you referred 0. Before 0 you referred 3. So 3 is the least recently used. Least recently used. 4 is just brought into the main memory. 0 is before 4 you referred 0, and next before 40 you referred 3. So that is the reason why you select 3 as a victim page and replace 2 with the 3. Likewise, in the least recently used, you need to know the past history. How can we know the past history? Okay. There are two solutions for it. One is a counter and the second one is a stack. So what is a counter? For each and every page, when you brought into the main memory, you need to maintain the clock time. You need to keep the clock time into the counter. For each page, for example, 7. 7 was referred at what time? That clock time will be you kept into the counter. Again, when you refer 0, so when will be you when was you referred the 0 last time? When was you referred the 0 last time? That is maintained by the counter. Like that, every page entry has a counter. Every time a page is referenced to this entry, copy the clock into the counter so that you came to know when was it last referred. Okay, and the next one is a stack. What is a stack? Whenever you referred a page, you need to keep the 4 into the stack, and then after that you referred 7, so you need to keep the 7 on the top of 4. Again you referred 0, so what you need to do? You need to keep the 0 on the top of 4 and 7. Again you referred 7. What you need to do? You need to shuffle the things. You need to keep the 0 after 7, and you need to keep the 7 here. Okay, and then 1 came into the main memory. Okay, and then 0. What you need to do? You need to move the 0 to the top, and you need to take down 1 and 4. Okay, so up to this point, what are the entries? 0 is the top one, and then 1, and then 7, and the last one is a 4. So after that again 1 came to the main memory. So what is the position of stack when up to this point? 1 0 7 4. 1 just referred, before that 0, and then 7, and then 4. Okay, at this position what is the stack value? At this position what is the stack value? So don't consider these two things. These two diagrams are at these positions, right? Otherwise, let me explain with the help of a paint. So, right. So, for example, this is the reference string. What's the problem? Right. So 1, 0, 4, 7, 2, 0, 1, 3, 5, 7, 2. These are the pages you want to use. So what you need to keep into the main memory? So 1 you keep into the main memory, and then on the top of 1 you need to keep, sorry, stack 1 you need to keep into the stack, on the top of 1 you need to keep the 4, okay, and then you need to keep 4 on top of 0. Again what you need to keep, and then you need to keep 7 on top of 4, and then you need to keep 2 on top of 7, right? So after that you require 0, right? Whenever you require 0, what you need to do, you need to take the 0 to the top position and you need to keep all these things down to 0, right? That means 1 and then 4 and then 7 and then 2 and then 0, right? So likewise you need to shuffle the things. Now this is the location and this is the location for 1, right? Check here. Now you require 1 and you are trying to refer the page number 1. So what you need to do? So whenever you refer the page now, earlier also you refer the page, the same page was referred by you right now. So what you need to do? You need to keep this 1 to the top of the stack. So 1, and next you need to keep all the remaining pages into the page, all the remaining pages down to the 1, right? Likewise, whenever you refer the page, that page will be the placed in the top of the stack, okay? In this particular order, which page was referred first? Least recently used, 4. Least recently used. Long back I have used that one. After that 7 I have used. After that 2 I have used. After that 0 I have used. And then right now top of the stack indicates most recently used page. Likewise, I can know which page was referred at what time. Okay. So likewise, I can maintain the past history of page references by using a stack. Okay. And the second technique I already told you, that is a counter. Whenever you refer a page, you need to maintain the clock time into the counter. For that every page there is a counter, right? Whenever you refer page 0, you need to keep the details into the counter. Likewise, counter is used to identify the time when the page was referred by us, right? That is the thing. And then LRU approximation. So reference bit and second chance algorithm. What is a reference bit and what is a second chance algorithm? So actually whenever you want to refer the page, each and every page has a reference bit. Each and every page has a reference bit. So initially the reference bit is set to 0. Initially the reference bit is set to 0. So whenever you refer the page, for example page 0 is referred, now there are total 3 pages. Each and every page reference bit is initially 0. So for example, you refer the pages like this, right? So whenever you refer the page, automatically this reference bit will be set to 1. Page 1 you referred, and next page 3 you referred 1, and next page 0 you referred 1. Likewise, whenever you refer that particular page, automatically the reference bit will be changed to 0 to 1. Okay, whenever you want to choose a victim page, which page you need to choose as a victim page? Second page is not referred by you, so that is the reason why you can choose the second page as a victim page. Why? Because it is not referred. Okay, it is not referred, so the reference bit is 0 for the page 2. So the page 2 will be selected as a victim page. It is not that important when compared to page 0, page 1 and page 3. Okay. So there is a enhanced second chance algorithm under the LRU. So what is enhanced second chance? Enhanced second chance means whenever you want to consider as a victim page, you need to give it as a second chance. You need to give the page as a second chance. For example, so these are the references bits, right? So these are the pages. Otherwise better you keep one here. So whenever you want to replace all are ones, you will select this page as a victim page. What the reference bit? This is the reference bit, right? So whenever there is a reference to this particular page, the reference bit is 1. So you need to select this page as a victim page. But what is the reference bit? The reference bit is 1. So whenever the reference bit is 1 and you want to select it as a victim, better to give a second chance. Better to give a second chance to that particular page. So you convert this particular 1 to 0 and you move to this particular place. Again the reference bit is 1. So you need to keep it 0 and you need to give this page as a second chance. Again you need to move to the next page. There you need to convert a 0 bit 1 to 0 and then move to the next one. Again 1, so 0. If it is 0, you can choose this page. If it is also 1, what you need to do? So again you need to keep it as a 0 and move back to the starting page. So you need to come here, again the space is 1, so 0. And next whenever you come to this particular place now, earlier you was already given a chance to this particular page. So choose this page as a victim page. Like that, if the reference bit is 0, you can choose it as a victim page directly. Okay, if the reference bit is 1, then what you need to do? You need to give a second chance. You need to give a second chance to that page, right? Why? Because it is referred by you. That means it might be used for you. That is the reason why the second chance algorithm will don't select a victim page whose reference bit is 1 for the first time. Okay, so whenever you want to select that page as a victim page, if the reference bit is 1, please give that page a second chance. Okay, so convert the 1 to 0 and move to the next page. If it is also the reference bit is 1 for the next page, move to the next page. Like that you need to consider all the can check the all the pages in the round robin fashion. Okay, so that is called as second chance algorithm, right? And the next one is enhanced second chance algorithm. What is enhanced second chance? This is second chance algorithm, right? And then what is enhanced second chance? What is enhanced second chance? Enhanced second chance means if up to now we are considering only the reference bit, but you need to consider the reference bit as well as modified bit. MB means modified bit. Reference bit as well as modified bit. So the reference bit is 0 and the modified bit is 0. This is the page which is having the reference bit 0 and the modified. Modified means you done some modification to that particular page. You did the modifications. So there is a no modifications and that page is not referred. That page is the best page. Best page for victim. Okay, you can select that page as a victim, best suited for the victim page. And then the next one is 1 comma 0. That means it is referred but not modified. What is 0 0? 0 0 means not referred, not modified. What is 1 0? 1 0 means referred but not modified. Referred but not modified. This is the next best after 0 0. What is the next page? 0 1. 0 1 means not referred but modified. Not referred but modified. What is the last pair? 1 1. 1 1 means referred unmodified. So you are referring that page and you are modifying that page. So this is the page should not consider as a victim page. Okay, what is the first best to consider as a victim page? The page which was not referred, not modified. It is the best one as a victim. And next one is a 1 0. That means referred, not modified. After that, not referred but modified. Okay, and next referred, modified. So these are the things comes under enhanced second chance. Up to second chance we have considered the only reference bits. But in the enhanced second chance, we need to consider the reference bit as well as the modified bit. So there are total 4 combinations. Among those, 00 is the best page for considering as a victim, and next 11 is the worst page considered as a victim. That means you should not consider the page which is having the reference bit 1 and the modified bit 1 as a victim page. You should not consider as a victim page. Okay, this is called as enhanced second chance algorithm. And the next one is a counting algorithms. What is counting algorithms? So there are two types of counting algorithms, LFU, MFU. LFU means the page which is the smallest count and just came into the main memory. Okay, replace the page with the smallest count, that will be considered as a victim page. What is the most frequently used? That means the page with the smallest count need to be there in the main memory because it might be used in the future. Are you got my point? There are two types of counting algorithms. One is LFU and the second one is MFU. LFU means least frequently used. LFU means least frequently used. MFU means most frequently used. So what is the difference between least frequently used and most frequently used? Least frequently used means the page which was just brought in will be considered as a considered as a victim. That means it is just enter into the main memory. So you need to select that one as a the page which was just enter into the main memory. You need to consider that as a victim page. Why? Because you already referred that one, so it might not be used in the future. Just you already used that one, so you might not use it in the near future. That is called as least frequently used. So what most frequently used? It is a reverse of least frequently used. The page which was just brought into the main memory might be used in the near future, might be used, later. Why? Because later in the near future, later in near. Why? Because the page is just brought in into the main memory frames. The page is just brought into the main memory frame. Okay, just brought in means just you referred right now. It might be used multiple times later also. So that is the reason why the page should not be considered as a victim page. That is called as least frequently used and most frequently used. Read on the lines once. Replace the page with the smallest count. Okay. And next, what is most frequently used? Based on the argument that the page with the smallest count was probably just brought in. That means the page with which page is came into the main memory just in, that page will always get the less count. Okay, that page will be used in the near future. It is just brought in and it has yet to be used. It may be used in the near future. So that is the reason why we should not select it as a victim page. Is it clear now? Is it okay now? Is it okay? Okay then. Right? So that is the difference between least frequently used and most frequently used. The page replacement algorithms are very much important for you as of my knowledge, and there is some complexity is also there. That is the reason why. So I have discussed that particular replacement algorithms from the last two classes. Okay. And the next one is page buffering algorithms. So what are the page buffering algorithms? When there is a frame available, when needed. So when the frame is available, there are pool of free frames in the main memory. whenever the free frame available when needed. So no need to not found at a fault time. That means whenever there is a what you called page fault, and if there is a free frame, you can keep the page into the free frame. If the free frame is not found, what you have to do? You need to select one victim page and you need to keep the page into the main memory. Okay, so possibly keep a list of modified pages. So whenever you are moving in particular page from main memory to the second memory, so what you need to do? You need to consider some things anamata. So what are those? Whether that particular page is a modified page or that particular page is a referenced page before reused. That means that page is referenced and modified. I already told you, if the page is referenced, if the page is referred and if the page is modified, then what you need to do? That page should not select as a victim page. I already told you, whenever you are selecting, whenever there is a page fault, if there is a free frame, you can keep that particular page into the free frame. There is no problem. Whenever there is a requirement of a page and there is no free frame, so automatically what the problem? No free frame is there means you need to select one page as victim page. Okay, you need to take this page from the secondary main memory to the secondary memory and you need to brought into that particular page, into the page 0 into the main memory, right? So whenever this happened, if there is a page fault and there is no free frame, at that time you need to consider the reference bit as well as the modified bit. Okay, before consider the page as a victim page, you need to check whether it is referred and modified or not. Okay, that is the thing you need to consider, right? And then there is a concept called as thrashing, and the next concept is called as allocation of frames. Okay, this is the next topic. What is thrashing? Thrashing means high paging activity. High paging activity is called as thrashing. Okay, and next, what is allocation of frames? Meanwhile, remember this point, high paging activity is called as thrashing. Remember this point. Later in detail we'll discuss about thrashing. And next, what about allocation of frames? There are two types of allocation, that is equal allocation and the second one is proportional allocation. Equal allocation and the second one is the proportional allocation. What is equal allocation? What is proportional allocation? So for example, there are 50 frames in the main memory. 50 frames in main memory, there are 50 frames. Number of process are 10. Okay, what the equal allocation says that, so as there are 10 number of process and 50 free frames are available, divide divide the frames equally and assign to the process. So if you divide the frames to the 10 process equally, each and every process will get 5 frames. Why? Because 50 by 10 means 5 frames. Each and every process will get 5 frames. That is called as equal allocation. That means all the available free frames are allocated to the number of process in a mission equally. So that is called as equal allocation. Okay, what is the problem with the equal allocation? So for example, there are total 12 free frames. Let's say 12 free frames, and there are 3 processes in the machine, P1, P2, P3. Actually, P1 requires only 2 frames. Why? Because P1 is divided into 2 pages. and next P2 is divided into 4 pages, and P3 is divided into 6 pages. Okay, these are the frame requirements for each and every process. Actually, how many frames are required for keeping a P1 into the main memory? We require 2 frames. How many free frames required to keep the process 2? We require 4 pages. How many process we require for P3? 6 pages. How many number of free frames are available? 12 free frames. Okay. So, but what the equal allocation will do? The equal allocation will do, it will give P1 4 frames and P2 4 frames and P3 4 frames. It divides the number of free frames into by number of process. 12 is the free frame and 3 is the number of process. It is 4. That means it will allocate 4 frames. 4 frames to each process. What happened if we assign 4 frames for each process? By using this example, we can say that, so P1 requires only two frames in order to keep the 2 pages, but we are giving 4 frames. What is the wastage? 2 frames waste. And next to page 2 require 4 pages, we are giving 4. So no problem here, no wastage. And next P3 require 6 pages. But how many pages frames we have assigned to that particular P3? 4 frames. That means 6 minus 4. That means still it require 2 free frames. Okay. That means some processes are small and some processes are big. Okay. If we assign more number of process if we assign more frames to the small process, what happened? Frames are not utilized. Frames are not utilized completely. Why? Because here the P1 require only 2 frames in order to keep the 2 pages, but you are allocating 4 frames to it. So 2 frames are not utilized, right? If it is a big process, for the big processor also you are assigning only 4 frames in this example, but the big process P3 requires 6, but you are allocating 4. Okay, that is the problem with the equal allocation. Okay, in order to avoid such a problem, we will move to the proportional allocation. Okay, what is proportional allocation? What is proportional allocation? What is proportional allocation? Proportional allocation means based upon the size of the process. Based upon the size of the process, we need to assign the free frames. For example, if it is a small process, we assign less number of free frames. If it is a big process, we are allocating more number of frames. Okay, so that is called as proportional allocation. That means based upon the size of a process, we are assigning the frames. Okay, are you got my point? So consider one example. Consider one example. Okay, so whenever there is a formula for the proportional allocation. AI equal to Si by S into M. Okay, capital S, this is a capital S. Capital S means sum of sizes of all processes in the machine, right? Capital S. And then, so what is M? Okay, M is number of frames, main memory frames available. Number of main memory frames available. Okay, and then, so for example, if there are two processes in a machine, P1 is of size 10 kb, and next another one is there, that is called as P2, which is of size 127 kb. So 10 is a small process and P2 is a big process. For example, in our system there are 62 frames. 62 frames. 62 frames are available in our machine. That is M equal to 62. So if it is a equal allocation, what it will do? If there are 62 frames available in your machine, if it is equal allocation, so P1 will get 31 frames and P2 will get 31 frames. Why? Because 31 plus 31 is 62. But in the case of proportional allocation, so what we need to do? So there is a process of size 10 kb and this is a process 2 of 120 kb, 127 kb. What I told you earlier. So depending upon the size of the process, we are going to allocate the frames. Depending upon the size of a process, we are going to allocate the frames. Okay. So how many number of frames we need to allocate for process 1? AI means the I value is 1 for P1. And next, what is the size of that particular P1? 10. 10 is the size. S1. S1 means size of process 1. Okay. We need to change the formula like this. Are you got my point? A1 means allocation of frames to process 1. So S1 SI means S1 by total size into M. Now calculate. A1 equal to, what is size of S1? 10. What is the total size? Total size means 10 plus 127. P1 size and P2 size. That means S1 plus S2 equal to 137. So 137. And next, what is the value of M? 62 frames. What is the value of M? 62 frames. So that if you calculate this one, A1 will get the 4 frames. That means for P1, we are giving only 4 frames. So what about the A2? That means allocation to process 2. Allocation to process 2. S2 by capital S into M. So what is the S2 value? S2 value is size of process 2. 127. 127 by, what is the total size? Total size capital S 137 into number of free frames 62. So how many what will get? Will get 57 frames. Okay, that means by using a proportional allocation based upon the size of the process, we are allocating the frames. P1 is of small size. By using this formula, only we can allocate 4 frames to P1. So how much size P2 is 127 kb. So it is a big process when compared to P1. So how many number of frames we need to allocate according to this formula? 57 frames we need to allocate to this particular process P2. Okay. So based upon the size, we are allocating the frames. So that is the reason why it is called as proportional allocation. Okay. And there is a topic called as global versus local allocation. And the next concept is global versus local allocation. Okay. What is global versus local allocation? Right? Whenever you have used a global replacement, what is local allocation and what is a global allocation? Give me 1 second, please. There is a call. Wait. Sorry. So what is a local allocation? Whenever a process needs a page which is not in the main memory. That means, for example, P1 is of 7 pages. P1 is divided into 7 pages. Now only five frames are allocated to the P1. Okay, so you can keep only 7 pages into the main memory. Out of 7, you can keep only 5 pages into the main memory frames. Right? So automatically what you have to do, now you require the 6th page. Now you require 6th page. Already you have allocated 5 pages to 5 frames. Okay. Whenever there is a requirement of a new page and that page is not in the main memory, so it can be bring into the new page and allocated to a frame from its own set of allocated frames. That means local means whenever there is a need of a new page, so what you need to do, you have to use the frames which were allocated to it only. The process should not use the frames which were allocated to the some other process. Only the particular process need to use the frames which was allocated to it locally. It should not use the frames which was allocated to the other process, even though they are free. Even though they are free. For example, there is another process called as P4. P4 requires actually three frames. Why? Because it is only divided into 3 pages, so it require only 3 frames, but you allocated 5 frames to it. So how many number of free frames available to P1? After keeping these 3 pages also, after keeping 3 pages into main memory frames, still 2 frames are available. 2 frames are available and they are free. Those frames are free. Okay. What here? P1 requires 7 pages, 7 frames, but we have assigned only 5 frames. So it requires 2 more frames to keep the remaining 2 pages. But P1 should not use the free frames which were allocated to the some other process. What the P1 has to use? P1 has to use the frames which was allocated to it. Okay, that is the thing. That is about local allocation. The process should not use the frames which were allocated to the some other process, even though they are free. Okay, so what is the disadvantage of this particular one? Even low priority process or high priority process, so both are having the same preference. Okay, so they cannot get more and they cannot get the low. With the help of low priority and high priority, so low priority process and the high priority process, both are not much difference for the local allocation. But whereas a global allocation, what is global allocation? For example, whenever the process needs a page into the main memory, it can bring the new page and it allocates it from the set of all frames. That means even that particular frame is currently allocated to the some other process. For example, here there are 2 frames, free frames, and which were allocated to P4 and they are free. So with the help of global allocation, any other process can access these 2 free frames if required. Okay, that means for this process, these 2 are not local, right? These 2 free frames are not local. Why? Because these free frames are allocated to the P4. But any other some process, for example, P3 or P2 can access the free frames which was allocated to the some other process. Okay. So that you can better utilize the main memory. That is the advantage. You can better utilize the main memory. There will be no free frames left in the main memory. If you keep more number of programs or pages into the main memory, so that if you keep the more number of pages into the main memory, automatically page faults will be reduced. Whenever the page faults will be reduced, automatically system performance will be increased. Are you got my point? So whenever there is a free frame which were allocated to some other process P4, P3 or P2 might require the 2 frames. Okay, they are not having the frames right now. What they can do, they can access the frames which were already, they can access the free frames which were already allocated to the P4. Okay, like that any other process can access the frames available to the other process. So then what is the advantage of this particular one? So we can keep pages into the main memory whenever there is a need. So automatically page faults will be reduced. Whenever the page fault on page replacement algorithm reduce, so automatically the system performance will be more. Okay, that is the thing. But what is the disadvantage? Disadvantage of global allocation. The disadvantage of global allocation is security. Protection, that means we cannot protect the main memory. We cannot protect the main memory. Protection issues will become. So why? Because any process can access the frames of any other process. That means here the high priority, any means high priority process can access the frames of any other low priority process, might be. So automatically what the problem, every time we are giving a chance to the high priority process, it can use the frames which were allocated to the low priority process. So high priority process, which process are using which frames, we cannot control the thing. So that is the problem. So that is called as memory protection issue. Okay, we cannot control axing of frames which are allocated to the other process. That is the problem with global allocation. So this is called as global and local. Local means the process has to utilize the frames which is allocated to it only. Okay, what is global? Then any high priority process can access the frames which are allocated to the low priority frame, low priority process frames. Okay, that is called as global. So here the memory utilization is more, but the problem is protection. We cannot control which process are using which frames, and that frames are allocated to the some other process, right? That is the problem with global. Okay, so that is about allocation of frames. Under the allocation of frames, you need to write about equal allocation and then proportional allocation, and you need to write about global versus local. And then what you need to write under the proportional allocation, you need to write the formula like this one. A means here allocation. Okay, if you want to calculate for P1, A1 equal to S1 by capital S into M. Here M is the total number of frames, S is the total size of all process. That means sum of size of all process. And next S1 is the size of a P1, size of P1. Like that you need to calculate the formula for each and every process. Based on that we can allocate the frames to the process. That is called as equal proportion and proportional allocation. Equal and proportional allocation. And then global versus local. Okay. So already we are running behind the time. So tomorrow we will discuss about trashing. Okay. Thank you. Is there any doubts? Let me know. Is there any doubts? So do you have any doubts? Let me know. In the page replacement algorithms as well as allocation of frames, or in the virtual memory, demand paging. Why? Because tomorrow you will wind up the third unit and you are going to start the next unit. That is the reason. Trashing will take just a few minutes, maybe 10 to 15 minutes. After that, we will move to the next concept. That is the fourth unit. So do you have any doubts? So let me know today. Respond fast, please. No doubts? Okay. Thank you.